Solar Systems 3209, Unit 2, Historical Geology. References can be found in Chapter 6, Chapter 8, Appendix A, and Appendix B. Unit 2, Topic 2.5, Radioactive Dating Problems. This presentation will focus on determining the age of a sample using radiometric data, and also demonstrating scenarios that include calculations to determine, number 1, the fraction or percent of parent and daughter material, number 2, the number of half-lives, number 3, the ratios of parent to daughter materials, and number 4, changing masses. When we look at radioactive dating problems, these questions can make reference to the radioactive parent isotope in 3 different forms. First form is we can look at the fraction of radioactive parent compared to the stable daughter product. In this case, for example, we have 1/16 of the radioactive parent left. 1/16 would mean it went through 4 different half-lives, and only 1 part out of 16 parts is actually radioactive parent. The second type of radioactive dating problem we'll study is percent form. In this example, we have 25% of radioactive parent remaining. Therefore, 75% of the sample must be stable daughter product. The third type of problem we will look at is the remaining parent in grams. For example, if we have 512 grams of parent remaining, and we know the initial amount of parent that was in the sample at the beginning, we can determine the number of half-lives. Also, if we know the number of half-lives, and we know a sample originally had 512 grams, then we can find the amount of material, radioactive material, that remains after a given number of half-lives. When you do a radioactive dating problem, first thing we need to do is figure out the number of half-lives that have passed. So when calculating any radioactive dating problem, you first need to calculate the number of half-lives. This is key to finding the answer to any radioactive dating problem. One piece of information that will be given in the problem will allow you to do this. For example, if you were given a fraction of 1/16 of the parent material remaining, we can figure out the amount of half-lives that remain. For example, if you have 1/16 of the parent remaining, that means that after going through a number of half-lives to get down to 1/16 remaining, we always start off with a fraction of 1/1. This means that 100% of the radioactive sample is parent. From here, we take 1/2 of the fraction. So 1/1 multiplied by 1/2 will give us 1/2 of parent remaining. Therefore, 1/2 will be parent, 1/2 will be daughter. If we go through another half-life, that means 1/2 of 1/2, we get down to 1/4. Note that the denominator in the fractions are always doubling. So if you take 1/2 of any fraction, therefore the bottom number, the denominator, will always double. So after another half-life, we know that 1/8 would remain. And then after another half-life, 1/16 would remain. So in order to figure out the number of half-lives that have taken place, we look at the number of arrows. If we count the number of arrows, 1, 2, 3, and 4, the arrows will tell us that this sample has undergone 4 half-lives. That's how we would use a fraction to determine the number of half-lives that passed. If we had a percentage provided, in this case 25%, we can do something similar. We always know that 100% of the original sample would be parent. After one half-life, half would be parent, 50% would be parent, and 50% will be daughter. After two half-lives, 50% of the material that's remaining will decay to one half its size to form 25%. So again, we count the number of arrows, 1, 2, and we know that this sample would have gone through 2 half-lives. If we look at a ratio, and in this example we see a ratio of 1 to 7, that means we have 1 part parent and we have 7 parts daughter. So really we have 8 parts in total. If we look at the amount of parent left, that would suggest we had 1 part out of 8 parts that are parent, which is the radioactive sample. Once we arrange it into a fraction form, we can find the half-life by doing the same process as above. And if we go above, we notice that to get to 1/8, you had to go through 1 half-life, 2 half-lives, 3 half-lives. So if you had a fraction of 1 to 7, 3 half-lives would have passed. So in order to do any radioactive dating problem, the key is in the first point. You need to find out the number of half-lives that have passed, and you can find that by the information that is given in the sample problems. Let's have a look at some of the different problem types, and you'll see what I'm talking about by finding the number of half-lives. Problem type number 1. If we look at the fraction of parent remaining, given that the half-life of uranium-235 is 0.7 billion years, determine the age of a sample of uranium-235 if 1/16 of the starting material remains. So as you read through the problem carefully, you'll see that different information is given in the problem. One part of information that is given in the problem is you have a half-life of 0.7 billion years. This is going to be important when you calculate the age of the sample. Also, we know that the sample has 1/16 of the starting material remaining. So if the starting material starts with a fraction of 1/1, then we can calculate how much of the sample remains after 1/16. To figure out the number of half-lives, we always start off with 0 half-lives. And if your sample didn't go through any half-lives, that means we have 100% of the parent that's radioactive. And a fraction that represents 100% will be 1/1. After the first half-life, 1/2 of the fraction would remain. So that would be 1/2. After second half-life, we get 1/2 of a half, which equals 1/4. After 3 half-lives, we have 1/8. So the amount of parent material keeps decreasing by 1/2 with every half-life. And after 4 half-lives, we are finally down to the percentage that was provided. That would be 1/16. So we know that our sample has gone through 4 half-lives. In order to calculate the age of the sample, we need to go back and look at the amount, what is given in the problem. We know that the half-life in this problem was 0.7 billion years. We know that the fraction in the problem was 1/16 of the original parent material remaining. So therefore, by calculating the number of half-lives, we know that the sample has gone through 4 half-lives when 1/16 of the parent remains. We use this information to find the age of the overall sample. Age of the overall sample is found by looking at the number of half-lives multiplied by the time for one half-life. In our situation, we know the number of half-lives was 4, and we multiply by that by the time it takes for one half-life. So if we look back at what was given, fraction being 1/16, and the time it takes for one half-life is 0.7 billion years. So we multiply 4.0.7 billion years. Once we multiply the number of half-lives times the time it takes for one half-life, then we end up with the age of the sample. So 4 times 0.7 would equal 2.8 billion years. And that would be the age of the radioactive sample in this problem. If we go and look at example number 2, the question reads, calculate the age of a rock using potassium-40 decaying the argon-40 dating method, which has a half-life of 1.3 billion years. So we know that the half-life in this case is 1.3 billion years, and we know that 12.5 of the original parent material remains. By looking at the information given, we know that the half-life of the radioactive sample is 1.3 billion years. The amount of parent material remaining is 12.5 billion years. So we can use this information to calculate the half-life. So the key to solving any radioactive problem, again, is to figure out the number of half-lives, and this is represented by n in the equation. To find the number of half-lives that pass when 12.5% of the radioactive sample remains, we can use a chart and follow the steps. First, the original amount before any radioactive material decayed, we got to note as 100%, because all of the radioactive material is present before any half-lives. This is represented in the chart as 0 half-lives. So we start out again with 0 half-lives, and our percentage of radioactive material will be 100%. Finally, we find how many half-lives the radioactive sample has to go through in order to have 12.5% of the original material remaining. So after one half-life, 100% of the material decays down to 50%. That would be one half-life. Now we have 50% of the material remaining as radioactive sample. After a second half-life, half of the 50% would decay. Therefore, we now have 25% of the original parent material as being radioactive. Then after a third half-life, 1/2 of the 25% would remain, which would be 12.5%. So the number of half-lives that it takes for the sample to get down to 12.5% would be 3 half-lives. Thus, in our equation, to calculate the age, our number of half-lives would be 3. So to calculate the age of a radioactive sample, we use the following formula. The age equals the number of half-lives multiplied by the time it takes for one half-life. And we know that the number of half-lives in our problem was 3, and the time it takes for one half-life will be 1.3 billion years. So to calculate the age, we just substitute those values into our formula. We know we have 3 half-lives multiplied by the time it takes for one half-life, which is 1.3 billion years. And 3 times 1.3 will be 3.9. billion years. So the age of this rock sample will be 3.9 billion years. Radioactive problem number 3. In this type of a radioactive problem, we're generally given the mass of the sample. The problem reads, 1,200 grams of radioactive element has decayed to produce 150 grams of the element. If the half-life of the material is 0.40 billion years, what is the age of the sample? So the information, once you read the problem carefully, that is given, it tells us that the original mass was 1,200 grams. After so many half-lives, which we don't know as of yet, it decayed to 150 grams. We also know that the half-life is 0.40 billion years. So first we need to find out the number of half-lives that have passed. Again, figuring out the number of half-lives that have passed is the key to doing any of these radioactive problems. And the information given in this problem, that we can find out the number of half-lives, we know the amount originally in the radioactive sample, before any of the radioactive sample decayed, was 1,200 grams. And we know that after a certain number of half-lives, we now have 150 grams remaining. So to figure out the number of half-lives, we take the original amount, which is 1,200 grams, and we break it down 1/2 its size, which represents each half-life. So 1,200 grams after one half-life would decay to form 600 grams. 600 grams would decay to form 300 grams. And 300 grams in turn would decay to form 150 grams. And 150 grams was the amount that was stated in the problem. That's the amount that remained after a certain number of half-lives. So again, when we want to figure out the number of half-lives, we count the number of arrows in between the numbers. And in this case, we have 1, 2, 3 arrows. So 3 arrows would represent 3 half-lives. So the sample takes 3 half-lives to break down, to go from 1,200 grams down to 150 grams. So once we know the number of half-lives equals 3, we can multiply this by the time it takes for each half-life. And in our original problem, it stated that the half-life of this sample was 0.4 billion years. So 3 times 0.40 billion years would equal 1.2 billion years. So 1.2 billion years will be the age of this radioactive sample. Let's have a look at some radioactive dating problems that were seen on past public exams. Example 1 states, what is the age of a rock described below? A granite sample is dated using radioactive isotope potassium-40, which has a half-life of 1.3 billion years. The rock contains 1/8 of the original potassium-40. So from the problem, we can write down what is given, and we know that K40 has a half-life equal to 1.3 billion years. We also know that the amount of radioactive parent that remains equals 1/8. So from this information that's given concerning potassium-40, we can get the number of half-lives by looking at the percent of parent remaining. As previously stated, the original parent, fraction of parent that's in the sample, will be 1/1. After one half-life, we have 1/2 of the parent remaining. After 2 half-lives, 1/4, and after 3 half-lives, 1/8. So again, when you look at calculate the number of half-lives, count the number of arrows. Here we have 1, 2, 3. So the number of half-lives in this case would be 3. Then you multiply the number of half-lives by the time it takes for one half-life, in this case 1.3 billion years, and that will give you your age of your sample. So 3 times 1.3 will be 3.9 billion years. So our answer in this case would be B. Your turn. Take some time now and complete the following questions. Solutions will be on the slides that follow, so you can pause your recording now, prepare your solution, and then resume the recording to check your answers. The question states, the half-life of element X is 200,000 years. If the sample originally had held 256 grams of parent isotope, and the rock sample has been determined to be 1 million years old, what mass of parent now remains? By reading through the problem carefully, we can see that the information that is given is as follows. We know that the half-life of radioactive element X is 200,000 years. We also know that the original amount, so the original mass that was present in the sample was 256 grams. That's before any of the radioactive sample had decayed. And in this case, the age of the sample is also given as 1 million years. So from this information, we have two pieces of information which will give us the number of half-lives. And if we look at the time for one half-life and the age of the sample, we can use this to calculate the number of half-lives that the sample has gone through. Once we know the number of half-lives that the sample has gone through, then we can break 256 grams down that many times, and that will give you your answer of how much mass will be left after 1 million years. So the solution to the problem says the half-life of element X is 2200 years. If the sample originally contained 256 grams of parent isotope, and the rock sample has been determined to be 1 million years old, what mass of the parent now remains? So again, to calculate the number of half-lives, we took 1 million years, which is the age, divided by the time it takes for one half-life, and we end up with 5 half-lives. Once we know that the sample has passed through 5 half-lives, we can then take the original mass and break it down 5 times. So once the mass is broken down 5 times, 256 grams form 128. Take 1/2, another half-life be 64 grams, another half-life 32 grams, another half-life 16 grams, and then a fifth half-life will be 8 grams. So again, we count the arrows, 1, 2, 3, 4, and 5. That corresponds to the number of half-lives. Therefore, the amount of sample remaining after 5 half-lives will be 8 grams. Your turn again. Take the time to prepare the solution for the following problem. The problem reads, the parent isotope of a radioactive element has a half-life of 250 million years. If a sample contains 12.5 of the parent isotope, how old is the rock? Show your workings. The solution to this problem, again, focuses on calculating your number of half-lives. What is given in the problem? We know that one half-life is 250 million years. We know that the parent isotope, radioactive isotope that is remaining, is 12.5 years, and we want to calculate the age. So the very first thing you need to do to find the age of the sample is we need to find the number of half-lives that have passed. We know that we started off with 100%. After one half-life, only 50% of your radioactive sample remains. Two half-lives, 25% of the radioactive sample remains. And after a third half-life, 12.5% of the radioactive sample will remain. So from this, we know that we have 3 half-lives. If we know there's 3 half-lives, we just take our 3 half-lives, multiply it by the time for one half-life, and that will give us the answer, which is 750 million years. When calculating radioactive dating problems, some of your common errors that people make when they do this type of problem is as follows. Students, when calculating the number of half-lives, as previously shown, they count to 0. They count to 0, which implies 100% of the sample as one of the half-lives. So, if you had a sample that started off with 100%, which decayed to 50%, which decayed to 25%, which decayed to 12.5%, and you counted to 100 as one of your half-lives, they could possibly make the mistake. They could say 100 represents the first half-life, 50% represents your second half-life, 25% represents your third, and 12.5 represents 4 half-lives. But in this case, as previously stated, we don't count the actual numbers, the percentages. Instead, we should count the arrows. So if we count the arrows, we will see that 1 half-life, 2 half-lives, 3 half-lives. So the correct number of half-lives would be 3 half-lives. And this is a common mistake made when students do this type of problem. So this will give an incorrect number of half-lives, which is 4, but the correct answer would be 3, by counting the number of arrows present. So in summary, the very first thing you should do when you want to calculate the age of any radioactive sample is find the number of half-lives. We find the number of half-lives by looking at the fraction of parent remaining. For example, 1 over 8 would tell us that we start off with 1 over 1, 1 over 2, 1 over 4, and 1 over 8. And if you count the arrows, 1, 2, and 3, we know that the sample has gone through 3 half-lives. If you look at a percentage of parent remaining, then we always start off with 100%, which decays to 50%, which decays to 25%, and so on. So you count the arrows, and we know that this sample has gone through 2 half-lives. Or if we look at a fraction, or a ratio, we change the ratio into a fraction, which we look at the total parts. So we know we have 1 part parent, 15 parts daughter, which is 16 parts total. From this, we take only the parent isotope, which is 1/16, and from 1/16, we figure out the number of half-lives by using the fraction method. Once you find the number of half-lives, then you can calculate what the problem's asking. The problem usually asks you to calculate the age of the sample, or it could ask you to calculate the mass of the radioactive material remaining.